Hello, welcome to Byju's JEE. I'm Himanshu Shukla, and today we are doing a video on the JEE paper which happened on April 8th, the Shift 1 paper. So what we're going to do is we're going to do an analysis of this paper, and then we're going to solve few really interesting problems that came in that paper. Now, while watching this video, if you find that you're genuinely learning something, then please do subscribe to our channel and press the bell icon and all that stuff. All right. So let's talk about the analysis of this paper. So usually mechanics and electromagnetism bears like a really good percentage in your paper. So there were in all 10 questions from mechanics and around 11 questions from electromagnetism, which is like a large number. Now from thermo and KTG, that is from thermodynamics and kinetic theory of gases, you have just one question. From waves and oscillation, again just one question. And from optics there were 4 questions, 4 nice easy ones. And again from modern physics you had 3 really scoring problems. Okay, so that was a quick analysis of how this paper was like. Now let's solve some problems from this paper. Now let's look at the next problem. Here there's a switch which is said to be closed at t is equal to 0, and you have to find the time after which the rate of dissipation of energy in the resistor is equal to the rate at which the energy is being stored in the inductor. Now that sounds a bit complicated. Let's see what it means. Now here what we have is a resistor as well as an inductor, and the rate at which the energy is being dissipated at the resistor is not equal to the rate at which the energy is being stored in the inductor. So we have to find at one particular time when they become equal. The first question is, why are they changing in the first place, right? If you simply had a resistive circuit, like a resistor with an EMF source, right, then in that case what would be the energy dissipated? It will be just I square R, right? I square R. Now that means that the heat is coming out at this rate. Okay, fine, that's interesting. Now I here is a constant, right? I is not changing in that case. But now what happens in this particular circuit when you have an inductor? What is the job of an inductor? Inductor tries to oppose the change in current. So initially the current was 0 and current wants to become its maximum value, which is E by R in this particular circuit. But the inductor is like, no, I'm going to oppose the change. So what the inductor ends up doing is it ends up slowing down the current. Right? It takes theoretically infinite time for the current to reach its maximum value. We have learned all this. So the current is basically changing with time in this case, right? So that is the most important thing that you have to remember, that in an LR circuit or an LC circuit, current changes with time. Okay, so this I is a function of T, right? Okay, so this here is the energy which is dissipated at the resistor. Now there's some rate at which the energy is being stored at the inductor. Now at what rate is the energy being stored at the inductor? That is given by the energy stored at the inductor, E, let's call it R, is given by the current times the potential difference across the inductor. Potential difference basically is the work done per unit charge. I is the rate at which the charges are coming. When you multiply both of them, you basically get an expression for power. And this is the power or the rate at which this energy is being stored at the inductor. Now, we have to find when these two guys become equal. Now, what is the potential difference across an inductor? Do you know that? Potential difference across the resistor, across an inductor is given by L times of di by dt. L is the inductance, di by dt is the rate at which the current is changing. Right? If di by dt was 0, then there would be no potential difference across the inductor. We know all that. Now basically I have to equate this to, right? That's what the question says. So let's do that. So I get I square R equal to I times of L di by dt. Okay, I can get rid of one of the i's. So what do I get here is IR equals to L di by dt. Now I know that I changes with time, but I don't know how exactly it does change with time. But I need to know that. Now I can actually sit here and derive how I varies in an LR circuit, right? I can do that, but you're not supposed to do that because you don't have that much time in your examination. So what would you do? So there's a mnemonic which I can tell rather, which might help you to remember these things. So in any LR or any LC circuit, right, either the current is increasing or it is decreasing. Those are the two conditions, right? If initially, let's say you had a capacitor, the capacitor was completely charged, then it will get discharged. So the current would finally the charge on it will become 0, so current basically decreases. In this case, there's a battery. Initially there was no current, absolutely 0, and the current is now increasing, right, from 0 to some value, and the inductor is trying to oppose that. So it is increasing slowly, but it is increasing. So either current increases or decreases. So see, there is this general expression, I is equal to I naught 1 minus e to the power of t by tau, right? This is the case when the current is increasing. This is an increasing function, and I is equal to I naught e to the power of minus t by tau. This is the case when the current is decreasing, and this is an equation which you can use for both LC or LR circuit, right? Only the difference will be I naughts might change depending on what your circuit is. Usually it is E by R, and your tau will change. For a CR circuit it is C times R, and for LR circuit it is L by R. Simple. So in this case the current is increasing, so I know I have to use this equation, right? So let's do that. Here, by the way, what is the value of I naught here? I naught is the maximum current, so here it will be E by R, right? So let's do that. So this will become IR, so that is I naught 1 minus e to the power of, minus t by tau, right? So minus t by tau, right, times R becomes equal to L times of di by dt. So there will be d by dt of I naught 1 minus e to the power of minus t by tau, right? This is what will happen. All right, so let's find this. So this becomes I naught 1 minus e to the power of minus t by tau times R equals to L times of, what is the differentiation of this? I naught comes out, it's a constant, and you get a e to the power of minus t by tau, and everything gets divided by a tau again, right? Because minus would get cancelled, and you get 1 by tau when you differentiate e to the power of minus t by tau. Okay, this has gotten a little clumsy, so let me take this on the next page. Now let's solve this. Here this I naught and this I naught gets cancelled. Good. Now I have 1 minus, and you have an R sitting there, so 1 minus e to the power of minus t by tau times of R becomes equal to L by tau times e to the power of minus t by tau. Alright, so this becomes, so what do I do now? I know that this tau is equal to L by R, so I can simply replace it by saying that it is L times of R, so it becomes this. That's very good, because L and R gets cancelled, so I get this good equation. 1 minus e to the power of minus t by tau becomes equal to e to the power of minus t by tau, right? So this becomes 1 is equal to 2 times of e to the power of minus t by tau, right? Or 1 by 2 is equal to e to the power of minus t by tau. Now you have to take log to the base e on both sides. This becomes alright, so as ln 1 by 2 equals minus t by tau, because you know log of e to the power of something becomes log of that thing, so it's clear. So log of 1 by something is just minus log of that, right? Becomes minus t by tau. That's okay, gets cancelled. So you get t equals to tau times ln 2. You know the value of tau is L by R. So now you know at this particular time, when time becomes equals to log to the base e 2 times of the time constant, the power dissipated by the resistor is exactly equal to the power or the rate at which the energy is being stored at the inductor. Here we have a problem where there are two identical containers of same emissivity containing liquids A and B, and the temperatures are same, 60 degrees Celsius initially, and the densities are also given to us, where density of A is less than density of B. Which plot best represents the temperature variation of both with time? So now both these objects are there, these liquids are there, right, at some particular temperature. Now what will happen? The emissivity is given. It means that of course they're radiating out their energy, right? And because of that, their temperature would fall, right? And you can see in all the four options we have temperature falling with time. That makes sense. Now which would fall faster is the question, and in what wave will it form? Will it be a linear like option number 4 or option number 3, or would it not be linear like option 1 or 2? Right? You have to figure that out. So let's see this. So the first thing that I know here is how am I going to approach this problem? See, the thing is, there's one equation I know, that the rate at which the heat is dissipated from any object is EA sigma T to the power of 4, where T is the temperature of that object, right? So if the temperature of that object is T, this is the rate at which it dissipates heat. But if the surrounding is at a temperature of T naught, then it is also gaining heat. But the rate at which it is gaining heat, that is dependent on the temperature of the surrounding, and that is equal to EA sigma T naught, or TS you can call it, to the power of 4. TS is a constant, so temperature of the surrounding doesn't change. So basically when you subtract this two, this is the heat lost, this is the heat gained. This will give you the total change or total energy which is going out of it per second, and that's what delta Q by delta T is, right? dQ by dt. Now here dQ by dt is fine. Now how does that relate to the change in temperature? Is it directly proportional, dQ and dt, right? As you increase as you change the energy of a substance, does the temperature also change? It does change, right? And how are they related? See, we remember that Q is related to T as Q is equal to ms delta T, or basically dQ is equal to ms delta T. The change in heat, or the heat given to a system or taken out of a system, is in this particular equation, it is the heat given to a system is equal to ms times dt, which is the change in the increase in the temperature of the system, right? When I differentiate this with respect to time, right, I see how dQ by dt is related to dt by dt. Now, but there's another thing, that here in this case, this dQ by dt, the rate at which this heat is changing, this is the heat which is going out of the system, right? However, this is the heat which is coming into the system, which is increasing the temperature. So if I have to use it here, then I have to put a negative sign in this equation, because this Q is not the heat which is getting into the system, it is the heat which is being lost from the system, right? So if I want to use this over in this equation, I get what do I get? dt by dt, with this negative sign going to the other side, I'll get EA sigma T to the power of 4 minus TS to the power of 4, and there's this negative divided by ms. That's what I'd get, right? So in this case, it is given that the rho of A is less than the rho of B, that is, the density of A is less than the density of B, but because the containers are identical, their volumes are same, that means that the mass of A should also be less than the mass of B, right? And the specific heat of A is given to be less than the specific heat of B. I can clearly see that SA is some 1000 and SB is some 2000. Now, M into S is a quantity which will be lesser for A than for B, right? So MS is less for A. What does that mean actually? What is M times F? M times S is basically the heat capacity of that object. What does that tell us? It tells us that to change the temperature of that object by 1 degree Celsius, I need ms amount of energy, right? If ms is less, it means that with less energy itself, its temperature can be changed by 1 degree Celsius. So in this case, dQ by dt is given same, right? Because the emissivity is same for both of them. Emissivity is basically for an object at a particular temperature, the ratio of the heat that it is dissipating versus divided by the heat that an ideal black body would have dissipated, right? So it's basically that ratio of how much percent it is ideal. That is given equal for both of them. So emissivity is same for both of them, right? A is same for both of them, sigma is same for both of them, it's a constant, T is same for both of them. So this entire numerator is same for both these substances, right? But ms changes. Ms is lower for A. So in this case, the rate at which the heat is being dissipated by both these objects is same, right? That means that, and it is given that A requires less heat to change its temperature. It means that, of course, A's temperature will change more, right? Because you're taking out the same amount of energy from both of them, right? At the same rate, but A requires less energy to be taken out to change its temperature. So A's temperature would fall faster than the temperature of B, right? So if both of these guys, they start from a particular point, right, say, so this is T and this is T, they both start from here, A would fall down in temperature quicker than B. So if this is where A will be, this is where B will be. But again, I'm not sure whether this will be a curved line like this or whether it will be straight line. I can be sure about that because I know that the slope here depends on the fourth power of temperature, right? If it were a straight line, then the slope would be independent of temperature, right? Because the slope would have been constant. But here the slope is not constant, so it's not a straight line, right? So if you look at the options, you can see that option 2 is the only correct option. So there are standing waves in both these rods, right? Now I know that this end, and this end, all these three ends are fixed. They can't move. So I know that these three ends have to be nodes. Now, so that means that this end is a node, this end is a node, and this end is a node, right? So the wave would look something like this, right? Over here, and if I draw it for this one, the wave would look something like this. Whatever, like, you know, I'm not sure. The frequency is the same, is what we are told. So the wavelengths need not be same. But the point is, this point, they are nodes. So there are there can only be some whole number multiples of the half cycles. So this is here is a half cycle. 1 half cycle, 2 half cycle, 3 half cycle, 4 half cycle. Like this, there are half cycles, right? There can be only a whole number multiple of that half cycle. It can only be like some 5 half cycles or 7 half cycles or 8 half cycles because the endpoints have to be nodes. Similarly here, so let's say this is N here and this is M here, right? Now, a half cycle has the length of a half cycle is lambda by 2, right? So here n times of lambda by 2 must be equal to its length, and here m times of lambda by 2 must be equal to the length of the thicker rod. Now lambdas need not be same, so let me call this as lambda A and lambda B, okay? And these are equal to its length, and length is given to be equal, so I can equate them simply. I can say that they are equal. Now what? Now get rid of this 2. So n by m, that is the ratio of the number of the half cycles that they have, is equal to lambda b by lambda a, the ratios of their wavelengths. Okay, now let's move ahead from here. Now what is wavelength? Wavelength is basically the velocity of that wave divided by its frequency, right? Because frequency times wavelength gives me velocity. Okay, cool. So the velocity of the wave in medium B divided by the frequency in medium B whole divided by the velocity in medium A divided by the frequency in medium A, right? That will be the ratio of wavelengths. Now the frequencies are given to be equal in the problem, so these two guys are equal, so I can just cancel them out, right? So what do I get? I get here VB by VA. So the ratios of their speeds, the speed of the waves, right? And what is the speed equal to? The speed formula is root over the tension by mu, mass per unit length. So here in this case tension will be same on both the rods, right? So here the mass per unit length for B will be, let's say, some mu B, and for A will be some mu A, okay? So this becomes root over mu A by mu B, mass per unit length. Here in this case we are given that the densities, the materials are same, so densities would be the same, right? But what would be the mass per unit length? So rho here is basically the density, right? So if I multiply rho with V, I get the mass, right? If I divide by L, I get the mass per unit length, right? So V by L will basically give me the cross-sectional area because AL gives you V, right? So rho times A would give you the mass per unit length, right? So let me do that. So here this becomes equal to under root of rho, which is same for both, times A. So area of A divided by rho times area of B, correct? So this becomes under root of area of A upon area of B, right? What would that become? So area here, the radii of is given, the radius of B is twice the radius of A. It means that the area of B would be 4 times because pi r square, right? So it will be under root of 1 by 4, that is 1 by 2. So the ratios of the number of half cycles that they have is 1 by 2, right? So if A has like some 5 half cycles, then B have like some 10 half cycles, right? That's what it means. But in each half cycle, you see there's one antinode, this peak over here, right? In each half cycle, there's one antinode. It means that the number of the ratio of their half cycles, the number of half cycles, would be equal to the ratio of their antinodes. Right? So the answer is 2. Now let's look at the next problem. Here we have a circular disk, and the surface density of this disk is given as rho naught times x, where x is the distance from the center. Right? And we have to find the moment of inertia of this disk about an axis perpendicular to its plane passing through its edge. And the diagram is given to us. Now, how would I do this? See, the first thing here is I see that the mass distribution in this case is not uniform. But if it were uniform, how would I have solved it? I know how to find the moment of inertia about its center of mass, right? That will be just mr square. In case of a disk, it will be half mr square. That's fine. But if I have to find the moment of inertia about a point which is at the edge, now that axis is parallel to the axis which is passing through the center of mass, right? You have to use your imagination. So I can use the parallel axis theorem here, which says that the moment of inertia about an axis which is parallel to an axis passing through the center of mass is the moment of inertia at the center of mass plus mr square. I could have used that. So in this case, I can't do that because the mass is not distributed uniformly, right? So what can we do? We can use integration again here. So let's do that. So here, this is the top view, right? Now, how am I going to solve it is the surface charge density is varying with x as you move from the center. So let me take from the center, let me take a ring, right? My diagram is not very good, but you can imagine, right? This is a ring here of some thickness, let's say some dx is a thickness, dx, okay, at a distance of x. Cool. Now, what would be the mass of this guy? What would be the mass of this tiny ring, right? That will be, okay, the surface charge density sigma times the area of that ring, right? The area of that ring would be how much? 2 pi x, which will be the circumference of that ring, times dx. That will give you the thickness of that ring, right? Circumference times the thickness, right? Because it's really tiny, we consider the circumference is same and all that, you know that. Now, this is the mass of the tiny ring, right? What would be its moment of inertia about its own center of mass? So about this point O. So what will be IO? IO will be nothing but dm, right? Times of x square, because that's the moment of inertia of a ring, mr square. So m here is dm times r is x, so dm x square. So that becomes sigma times 2 pi x times of dx times of x square, right? So what would be my I, let's call this some point A. So what would be IA, right? What would that be? That would be I naught, right? Plus the mass of the ring, which is dm, times r square. R is the distance between the two axes, right? In this case, this is the distance, which is r. So dm times r square, right? Simple. Now here I naught I have found it to be sigma 2 pi x dx times x square plus dm is sigma 2 pi x dx times you have an r square. That will give you the the small ia. Basically this for the small element, so I can write it as like dia. You know what's going on there. Now I'm going to integrate this on both the ends, right, to find the moment of inertia for the entire disk. I can do that because all this will add up. Now where the x will vary, x will vary from 0 to capital R, right? So value of sigma is also given to us here, right? The value of sigma is rho naught times of x here, right? So given that, now I can take things common. I can take 2 pi rho naught common out of this. So I get, what do I get here? Integration of, right? 0 to r. What do we get here is x to the power of 4 times of dx plus x square times of r square dx. That's what I get, right? And that's what I have to integrate. Now what does this become? This becomes equal to 2 pi rho naught integration of x to the power of 4 is x to the power of 5 by 5 from 0 to r, right? plus r square times integration of x square is x to the power of 3 by 3 again from 0 to r, right? So this becomes 2 pi times of rho naught r to the power of 5 by 5 plus r square times r cube by 3. That's very simple. So this becomes 2 pi rho naught r to the power 5 also I can take out to get 1 by 5 plus 1 by 3. What is 1 by 5 plus 1 by, that's like, right, 8 by 15, right? So this becomes 16 pi rho naught r to the power 5 by 15. And that is the correct answer. Let's look at this problem. A conducting sphere is enclosed by a hollow conducting shell, and initially the inner sphere has a charge of Q while the outer one is uncharged. Now the potential difference between the two spherical surfaces is found to be V. Later on, the outer shell is given a charge of minus 4Q, and you have to find the potential difference in the new case, right? So how are you going to solve this problem? Now here, this is the situation. You have a charge on the inner shell and the outer shell is uncharged, and the potential difference is V. Well, that potential difference would be because this inner shell here would be producing an electric field, right? So this is the way I see it. This is producing an electric field, right? And that E dot D is resulting in that potential difference between their surfaces. Now when you give it a charge of say minus 4Q or minus 8Q or minus 100Q or 1000Q outside, that new charge which has come on the shell, on the outer shell, doesn't create any electric field inside itself, right? You know that the electric field due to a shell, right, inside it is 0. So minus 4Q or minus whatever, what are the values, plus, minus, whatever charge you give to the outer shell, it doesn't contribute to any electric field inside the shell. So here this electric field still will be E, the distance between them is D, so potential difference still will just be V. So in this problem, there are 4 particles, each of mass m, and they're undergoing a circular motion under the influence of their own mutual gravitational interaction. So they're all pulling each other, and they're moving in a circle. While being at the vertices of a square of side A, so that's really interesting. So they're moving in a way that they're all moving in a circle, but when you join all of them together, you see like a square forming. Their speeds are what? First thing is I can say that they all would move with the same speed because this problem is beautifully symmetric, right? But how would I find the speed? So here they are all moving because of their own gravitational interaction, fine. But because they're moving in a circle, they must also have a centripetal force, right? That centripetal force must be provided on any individual mass. So that's what I'm going to do here, right? So here you see I have a very roughly made diagram. So let's see what is the net force acting on any of the masses. So let's take this mass, right? So this mass would have a force acting here because of this other m sitting. That will be like, let's say F, and here it'll have a force because of this m, right? And there will be a force like this in the forward direction because of this m sitting just opposite to this. So let's say call this A, B, C. So because of this A, B, C, there will be these 3 forces. I can say that this force here in magnitude will be the same as this force here. And what will that be? So let's call that force as F. That force F will be equal to G times M, Gm1, M2, mm by R square. So R is the distance between the masses. In this case, that is A. So this becomes Gmm by A square, right? And that's the same force here and here. What is this force though? That will be, let's call this F dash. F dash will be equal to G times of M divided by, I know this is A and this is A, and this here is 90 degrees. So I know that this distance will be the hypotenuse, that will be root over A square plus A square, right? So that's root 2A. So root 2A is the distance between this mass and this mass, and square of that will give you the force. Now these two forces, however, they're equal in magnitude, but they're not in the same direction. So I have to take the components of them in the towards the center, right? Why am I doing that? because I want to equate that to the centripetal force which acts towards the center, right? So that's what I'm doing. This angle here is 45 degrees, so the components will be cos 45s. So what will be the net force now? Net force will be GMM by A square. This guy, its cos component, that is cos 45 degrees. Then this guy plus GMM by A square, which is this person over here, this force, its cos component here, which is cos 45, plus this force over here, which is because of this mass, that is GMM by root 2a whole square, that becomes 2a square, right? This is the net force on any of the masses. This must be equal to the centripetal force, which is mv square by r here is root 2 times of a, that's the diameter, divided by 2, so that is a by root 2, right? That's the r. So let me do this. So this becomes, I can just take GMM by a square out of this, right, common, and I get 1 by root 2 and 1 by root 2. This becomes 2 by root 2 from these two expressions, plus 1 by 2, right, equal to mv square upon a by root 2, so that becomes root 2 divided by a, correct? Okay, so I can also cancel the m's here, so m and m would go away, so I get gm by a, and this root 2, if it comes here, I'll get 2 by 2 plus 1 by 2 root 2, right? This I've taken this root 2 over here, is equal to v square, right? So this becomes gm by a 1 plus 1 by 2 root 2 equals to v square, or v is equal to root over gm by a times root over 1 plus 1 by 2 root 2. Okay, but when I look at the options are given in decimal points, so I have to find that out. What would this be? So this I can write, okay, so 1 plus 1 by 2 root 2 is 2 root 2 plus 1 by 2 root 2, right? What is 2 root 2? 2 root 2 is, root 2 is like 1.414, so 2 root 2 is close to 3, right? So 3 plus 1, I can say this is like close to 4 by 3, right? 4 by 3, and I have to take the under root of that because everything is in an under root. So what is the under root of 4 by 3? Under root of 4 by 3 is basically 2 by under root of 3. Under root of 3 is 1.7, I know that. So 2 by 1.7, what would that be? 20 by 17, it will be 1.1 something, right? So you can see that option 2 is the correct option, right? Because it can't be 1.5 and it is 1 point something. So it is 1.1, whatever is the next digit, times root over gm by a. This is the speed with which they'll move. So in this problem, there's a conducting slider and the resistance of that is given to you as 10 ohms and the mass is 50 grams and the length is 10 centimeter. And it is kept on a U-shaped frame like that. And there's a uniform magnetic field as well, which is perpendicular to this frame, and the slider is attached to a spring also. The spring constant is given, and when the spring is displaced by A naught and released, at what time will its amplitude become A naught by E? Now that's a little it seems a little complicated. So what is happening here? So basically, if you just had the spring and something attached to a spring, and if you, let's say, compress it by A naught, right, then you know that the amplitude would just stay A naught, right? The amplitude wouldn't change. But in this case, what's happening, because this is a slider and there's a magnetic field, and you know that when a slider slides in a magnetic field, there's an motional EMF, right, which is equal to BVL, right? That's the EMF BVL, and that BVL would generate a current BVL by R. So what's happening here is that because of that current, this slider will experience another force. Now what happens is, see, when you have compressed the spring, right, the spring wants to like sort of speed up now, right? It wants to, it has a positive acceleration. From 0 it wants to speed up, but as it is trying to speed up, right, as the V is increasing, because I depends on V in this case, right, the force on that slider, because that depends on I, that force would keep on changing. So you understand this? Along with the with the spring force, there's another force because of magnetism, which is IBL, in which the I depends on V. So it means that the more the spring wants to move, the higher is its speed, the more would be restriction force from the magnetic field in order to trying to stop it. It's trying to restrict it in the sense that it is trying to apply a force in the opposite direction. So what will happen? The oscillation will get damped. It will not have the same amplitude as A. The amplitude would be now some function of time. Now how to find that? Let's do this problem now. So first let's see what is the force being applied by the spring, right? It is trying to pull this slider in this direction with a force of k times of x. So let's say this is the positive direction, this is the negative direction, that is minus kx, right? That's what it is. Now there's another force which is because of the magnetic field. Now for that I need to know the direction of I, in which sense is I moving. So for that I have BVL first of all, right? So B is inside, right, and V, this thing is moving in the forward direction, the velocity is in here. So what will be the direction of V cross B? So when you do V cross B, you get the upward direction. It means that the EMF in this slider, the positive polarity is on the upper side, right? The current would flow like this because that's the direction in which the positive charges are feeling the force, right? So it will come out like this and move right like this. So this is the direction of the current. Okay, now if you know now the direction of the current I, right, you know the direction of current, now you can tell what is the direction of the force, which is I into L cross B. So L is in the direction of I, so it is L cross B. When you do, you get again the same direction here, right? So you have to use your right hand thumb rule for this. So the force which the magnetic field is applying is minus IL times of B. Okay, so this is the net force acting on it. This must be equal to its mass times its acceleration, which can be written as d square x by dt square, right? Now there's a reason I have written it in this form. So what happens whenever you get a damped oscillation case for a spring, you should try to write your equation in this form. Now what happens? Now you can write this minus kx minus ILB minus m times of d square x upon dt square becomes equal to 0. So that becomes minus kx minus I is, I know from motional EMF that EMF is BVL, so I will be BVL by R, so this becomes BVL by R times of LB also sitting there minus m d square x by dt square equal to 0. So let me write that down again. This becomes minus kx minus V can be written as dx by dt, so minus d square L square by R dx by dt minus m times of d square x by dt square equal to 0. Now you see the point of me writing it in this form, because now I can compare it with the standard equation of a damped oscillation in case of a spring. So now I can compare this with the standard equation of a damped oscillation, and that's why I wrote it in this particular format. So that is kx plus b times of dx by dt plus m times of d square x by dt square equal to 0. Okay. Now when I do that, I can get the value of this b, which is very important. Okay, this is the damping coefficient. Now when I compare these two, I can clearly see that the value of b here is b square L square by R. Now you'd say, what's the point of getting the value of the damping coefficient? Once you get the value of the damping coefficient, now you can tell how the amplitude will change with time. So that expression is A is equal to A naught e to the power of minus b by 2m times of t. Okay, so this is how the amplitude changes with time. Okay, if you knew this expression, you would know that you needed b for this. To get b, you had to express the forces in this particular format and compare and get it. Okay, so that's what I have done. So this becomes equal to a naught e to the power of minus b square L square by 2mr times of t. It is given to us that a is equal to a naught by e, where e is that e, the exponent that we use, right, e to the power of whatever. So e is called the Euler's number apparently. So this is a naught by e. Okay, so now that's where we have gotten. Now this seems easy. Let's do this. So now this becomes e to the power of minus 1 equal to e to the power of minus b square L square by 2mr times of t. That becomes that L square, B square L square by 2 mr equal to 1 times T. So T becomes 2 mr upon B square times L square. So now when you put the values, right, the value of M to you is given as 50 grams. You have to convert it into kilograms. So that will become 50 into 10 to the power of minus 3 kilograms. R is given to you as 10. L is given as 10 centimeters. So that will become 10 into 10 to the power of minus 2 whole square, right? In this case, B is given as 0.1 Tesla. So this becomes 10,000 seconds. Okay, when you calculate that. So it takes 10,000 seconds for the amplitude in this particular case to becomes A0 by E. In this problem here, we have a ship A which is moving with a velocity of 30 I cap plus 50 J cap from the position 0, 0, that's the origin. And there's another ship B which is moving with a velocity of minus 10 I cap from a position of 80, 150. Now the time of minimum separation is like after how much time would these two ships will be at the minimum of their separation. Okay, let's try this problem. So now here is the situation. This here is the velocity of the ship A. This is the velocity of ship B. These are the positions, right? So if I draw this, I get something like this, right? This is my ship A, which is moving with some 30 I cap plus 50 J cap, like something like this, right? And ship B is at some point over here, let's say, I don't know, and it is moving over there with minus 10 I cap. Okay, and we have to find at what point they are at their closest, at after what time. Now to solve this problem, see, you have to either like consider the motion of both of them, right? You have to like consider the motion of both of them moving, right? And how they're going to like, you know, move past each other. Or you can reduce this problem to the motion of just one particle by using the concept of relative velocity. What you can do is, you can say that, okay, now ship A, let me consider the ship A does not move. It means let me see how the ship B looks from the ship A. Okay, so whenever you do VBA, it means that you have considered A to be stationary, and from there you're observing B, right? So what is VBA? VBA is VB minus VA. So what would I get? If you do this minus this, you get minus 40 I cap minus 50 J cap. Okay, so this is the relative velocity of B with respect to A. So now I have fixed A to where it was, which is at the origin 0, 0. I have made its velocity to be 0, and I have given its velocity in a sense to B. So from A, when I look at B, B seems to be moving something sort of like this, right? Now it's easy to find how much time it will take for this minimum separation. So how will I do this? So this guy here, because the velocity is in this direction, it will keep moving like this. So this point here is the point of minimum separation, this point here, right? This is the minimum separation. How much time does it take to reach this point? Let's call this point minimum separation, say M, right? From this point B, how much time does it take to reach M? That's what we have to find out. All right. Now, how can I go about that? So this distance here, let's call this distance, let's say some D, right? If that distance is D, and if I can somehow find this angle theta, right, then I can say that this angle here, this distance here, will be some D cos theta. And if I divide that D cos theta, the distance traveled, D cos theta, right, by the speed of B with respect to A, that is VBA, right, I'll get the time. It's easy as that, right? Now D is easy to find out, right? D is just the distance between B and the origin, and I know B is the point 80, 150, so that's easy to find. But what about this cos theta? What's the angle between these two lines? All right, so to solve that, there's this method which we can use. You see, this here is our D vector, right? That's the position vector of B from where it had started. And this here is the velocity vector, right? You can see that theta is basically the angle between the negative of the D vector. So if I call this as D vector, right, this one, then this here is the negative D vector. So theta is the angle between the negative D vector and the velocity vector, right? So how can I, if you have two vectors and you want to find the angle between the two vectors, what's the best way to do that, right? The word is dot product. So let's do that. So here I'll get this is equal to d, the VBA, that's cool. Now this cos theta can be written as the dot product between the minus d vector and the VBA vector. So two vectors. So this will give you the magnitude of d, magnitude of VBA times cos theta, right? If I divide it by their magnitude, that is d times VBA, what would I get? I'd get the value of cos theta, right? So that's what cos theta will be. So nice, this d and this d would get cancelled, all right? And this will become equal to, well, now what will be minus d dot VBA? So minus d is, what is minus d? So minus of, what is this d vector? D vector, this is 80, 150, that's the position vector. So d vector will be 80 I cap plus 150 j cap. Now that is dotted with VBA, which we have found out to be minus 40 I cap minus 50 j cap. Cool. All right, nice. Divided by VBA becomes squared. So what is VBA? It's the speed, right? That's the magnitude of this vector. So that is 40 square plus 50 square under root squared. Cool. So that we have gotten. Now, what's the dot product? We know how to find dot product. I dot I is 1, I dot j is 0 because they're perpendicular to each other. So this becomes, and there's negative also, all right. So this will become minus 80 minus into minus 40, it will become 80 times 40, right? And plus 150 times 50 divided by 40 square is 3600, 50 square 2500, that's like 4100, yeah. So that's 4100, right? That's what we'll get. 80 times 40 is, okay, so this is a calculation, 3200 plus 7500 divided by 4100. So that's just like, let me take it over here. All right, what will that be? 75 plus 32 will be 107, and 0 zeros would cancel by 41. That'll be how much? 41 2 times is 82, and then you get 25. That'll be like close to 6 times. So the answer is 2.6. So it'll take them 2.6 units of time to be at minimum distance from each other. So in this problem, you're given a converging lens of focal length of 20 centimeter and is placed between an object and another concave mirror, and the focal length of that mirror is also given to you as 10 centimeters. Now, where is the final image is? So you have 4 options, whether it's coinciding with the object, enlarged, inverted, real, and all that thing. See, I look at these 4 options and I see that all the 4 options have this thing in common, that coincides with the object. It kind of makes me think that, okay, do I really need to do calculations to, like, actual mathematics to solve this problem? Can I solve it using some trick? And says not trick exactly, but can I solve this problem using my brains a little and not actually going into the mathematics? So let's see this. So now here is the object. The focal length of this lens is 20. It means that the object is placed at 2f. 2f means when an object is at 2f, the image also forms at 2f on the other side of the lens. It is inverted and of the same size. So I know that the image for this guy would form here, right? Like this. It is inverted, it is of the same size, and it is at the same distance. So this distance here is 40. Okay, that's cool. Now this image is going to act as an object for the mirror. Now what is the distance? So this is 40, the total is given as 60, so this distance here is 20. I know that the focal length of the mirror is 10. So it means that this object is now placed at the center of curvature. I know for not the lens, for the mirror I mean. I know for a mirror, when an object is placed at the center of curvature, then the image is also formed at the center of curvature, which is inverted and of the same size, right? So inversion of this would mean that the image would be formed upright like that at the center of curvature of the same size. So this one is an image of this, and this is an image of the below one, right? Now that image would serve again as an object for the lens, right? Because the light would again come back to the lens. So this is the object for the lens now, which is at a distance of 40 centimeter, which is 2f for it. So the image will be formed again at a distance of 2f from the lens on the other end. It means its image would form over here like this, inverted compared like with respect to this. So here we see that the image is formed at the point where the original object was, and it is inverted of the same size, and it is real because the rays would actually go and meet there, right? In this particular problem, you're given two particles that are moving perpendicular to each other with some de-Broglie wavelength, which are lambda 1 and lambda 2. Now, if they collide and stick, then the de-Broglie wavelength of the system after collision will become what is what you have to find out. Okay. So when I see this problem, so what is happening here is that, let's say you have a particle moving in the upward direction, okay, with the de-Broglie wavelength lambda 1, and you can say the momentum h by lambda 1, right? That's the momentum. And here's another particle which is moving, let's say this way, right? And its momentum will be, let's say, h by lambda 2, because the de-Broglie wavelength is, say, lambda 2. Now both these guys would hit each other, let's say over here, and after hitting they just stick and they move together. So let's say they are moving together with some final momentum p. Okay. So okay, to solve this problem, because these two are moving in different directions, the easiest way is to take the coordinate system, right? I can say that when they stick together and they start moving, the momentum will still be conserved, right? So I can do that. So what is the momentum of this guy? It is h by lambda 1, right, times of j cap, because it's moving in the upward direction. What's the momentum of this? Plus h times of lambda 2 times of I cap. This is the net momentum but they had before collision, just before collision. This should be equal to the final momentum which they have p, right? So how would I find the magnitude of the final momentum? So if I want to find the magnitude of the final momentum, magnitude of p will be equal to, right, so these two are perpendicular to each other, so I can directly write under root of h square by lambda 1 square plus h square by lambda 2 square. So this becomes h times of under root of 1 by lambda 1 square plus 1 by lambda 2 square. So this is the final momentum. Now when they have a final momentum together, they'll also have a de-Broglie wavelength, right? And that de-Broglie wavelength will be h by, let's say, some lambda. So this is equal to some h by lambda, right? So I can find the value of lambda, right? So lambda will become equal to root over or 1 upon root over 1 by lambda 1 square plus 1 by lambda 2 square. So what will that become? This will become lambda is equal to okay, this will go up and this will be 1 upon under root of lambda 1 square plus lambda 2 square upon lambda 1 square lambda 2 square. Okay, and that will go on the top, so this will become lambda. So let me write it over here. Lambda becomes equals to lambda 1 lambda 2 upon under root of lambda 1 square plus lambda 2 square, and that is the right answer.
For more videos and live lectures on the JEE, click on the subscribe button now.